Hello all. So today I need to start a new topic, that is calculus. Very important topic again, and we have to use calculus in our machine learning, deep learning, generative AI. Okay. So what this calculus is? Well, a calculus is an abstract theory developed purely formal way, and calculus is analysis used in mathematics to study the rate of change. Okay, in general, we are talking about rate of change is calculus. Okay, so if you want to interpret slope of a curve, length, area, volume of the objects, we do use concepts of calculus. You already know that it comprises of differentiation and integration. Two things are present in the calculus. Okay. Calculus. That means what I mean is calculate. You need to calculate something. Okay. How? How you want to calculate something. And this calculation is not only over a simple kind of problems, but we do use this concept in complex problems. As told, area, volume of the objects. We may have irregular objects. For regular, it is quite easy to calculate the area. Area of a square is a square. Volume of a cube is a cube. But what for irregular objects? How you will calculate the area? Also, if I need to talk about rate of change, that is what a part of calculus which we say as differentiation. That is d by dx. That is the differentiation. So rate of change of y with respect to x. That's what we say. So we are having two quantities, x and y. What is the behavior of them? So in order to study the behavior, we do apply rate of change. Okay, and many in physics also, in maths also, we do have rate of change concepts. Okay, like if I would say velocity is rate of change of displacement with respect to time, and acceleration is rate of change of velocity with respect to time. So something like this we are having. Okay. So yes, we do use these concepts like differentiation, integration. And the word calculus came from a Latin meaning small stone, because it is like understanding something by looking at small pieces. Okay, whether differentiate is to divide, integrate is to combine, but division also is in for small pieces, and combination will also be of small pieces to make a big. Okay, both we are doing for small pieces. So calculus in Latin means small stone. Okay, so calculus is a part of maths, and in machine learning algorithms we do use calculus, and we cannot skip this topic in both data science and machine learning. Okay, in machine learning mostly the calculus, the differentiation is used. Okay, differentiation is highly used. especially for optimization. We'll be having an equation like this: w dash is equal to w minus alpha del L by del W. This is a equation which is used in neural network. Okay, where we want to update the weights of neurons. So this equation is used, and you can see differential partial differentiation is applied here. Okay, in machine learning also, so we will be starting our linear regression. There, I will be using this calculus. Okay, because in linear regression, we will be dealing with mx plus c. What is m? Slope. And what we call as a slope? What is slope? That is dy by dx. That's what the slope is. All right. So differential calculus cuts something in small pieces. Integral again join it, and we are having this term. Yeah, that's what I'm saying. Gradient descent. Gradient descent. That means how much the output of a function changes if the inputs a little bit. How output changes if we input something. Okay, for example, we are having a ball and a bowl. No matter wherever you slide the ball in the bowl, it will eventually land at the bottom. Okay, so you are having a bowl. This is a ball. It will go to the bottom. Okay, it will do some oscillation because of the velocity, and at the end, it will be present at the bottom. All right. Certainly, with this equation, with this curve equation, z equal to x square plus y square. Okay, the movement of ball is shown. Okay, so z equal to x square plus y square. It is having like x also, y also. Both the components are there. Okay, fine. And then here we can see a ball is following a path. Okay, it's a path which is followed by the ball. We can also say that ball is descending. It's going towards the bottom of the ball. Okay, and we can see that the image, the red lines are gradient of the ball, and the blue lines are the path of the ball. As the path of the ball slope is decreasing, it is called as gradient descent. We are having red and the blue. Red, you can see, like, okay, these tracks are being built. Okay, that is red. Okay, that is your red lines. These are the gradient of the ball at every position. Okay, for example, you were having ball at this position. Now ball came at this position, this position, this position, this position, this position. So let us consider these are the points. So you are calculating the gradient, okay, of ball at this particular point. And since you are having, you can say z equal to x square plus 2y square. That's what you are having as an equation. Okay, that means a second order equation, and we are having x and y both as the components. So obviously here partial differentiation will be applied. That means del z by del x, del z by del y. Partial differentiation will be applied. So when we are going to differentiate with z by x, then y will be constant, and when we are going to differentiate with y, x will be constant. So the values will be like del z by del x, it will be 2x, and here it will be 4y. And whatever be the coordinate are there, for example, this point, like whatever be the x values there, whatever be the y, just put it. Okay, fine, just put the values. Whatever be the coordinates are, put the values in x and y. Okay, so that's what it is telling. It's called as gradient descent. Differentiation, partial differentiation, it's called as gradient descent. Gradient descent. Now, one more thing. This is gradient actually. Gradient is d by d x. This is gradient. Descent means, okay, going down. Descent means down. Actually, now I want to tell one thing. Whenever gradient is calculated, now it is in above, not down. Gradient is always pointing towards upward. Descent means downward. So for a descent, now we put a minus sign. Okay, we put minus sign for descent. Okay, that's what we do. So this is gradient d by dx. We are talking about gradient descent. Descent means gradient is getting less. See the line they have mentioned, I guess. Uh, Blue line is the path of the ball, and as the path of the ball slope is decreasing, slope is decreasing. What is slope? Dy by dx. This is the slope. It is decreasing. As you are going down, it is decreasing. And because it is decreasing, that's the reason I have put minus sign. Descent. So remember, gradient descent negative, slope decrease हो रहा है. Okay, in our machine learning model, our goal is to reduce the cost of the input. That's what we will learn. What is this cost and everything are there. Ultimately, cost, it is talking about the error. Okay, so we need to reduce the cost. We need to reduce the error. So we do perform the optimization, and for that we do perform this your gradient descent calculation. We do there. Okay, so let us suppose if this is your data, John, Eve, and Adam. These are the marks which are present in the subjects, and their profession, what they are going to be, is predicted by the model. Okay, here John and Eve, they are going to be like doctor and engineer. Adam, it is not mentioned what it's going to be. Okay, so now if you think of the marks in the subject as a gradient and profession as the bottom target is the subject. Okay, now we think of marks in the subject as a gradient and profession as the bottom target. Profession is the target actually here. What they want to select. Profession is the target. And marks are your variable. And this is your target, what they want to achieve. So we are going to train our model on the basis of this. Okay, so that your model should predict what should be the profession Adam is going to choose ahead. So we'll take all this data. Okay, this also target put into the model for training, and then your model will let us know what Adam can become. Okay, so using John and Eve data, we can create gradient descent and tune our model, and then we can feed it the marks of the John inside it, and my model will give the prediction. That's what happens. So here, this is kind of a supervised learning that I will teach ahead. Supervised, that means you are having data along with you are having target. So we will train our model on the basis of these two. Later on, we will put, once your model got trained, you will fill the values with this and you will get what could be the result. Okay, fine. So yes, gradient is applied here. Fine. And this is a gradient descent of z equal to 10x square plus y square. That's what it is showing. You can see in a 3D plot. That means it's showing the oscillations. This point, then here is the gradient, then this is the gradient, then this is the gradient, and so on. And later on, it will be coming at the bottom. Okay, so gradient is keep on reducing, it's keep on decreasing. Okay, fine. So you started from here. Maybe your ball roll down because of velocity, it touches here. Then again, your ball, because of some velocity, touches here. Then it loses some velocity, again it present here, then again it is present here, then again it is present here. Slowly, slowly, it will go to the bottom. Okay, fine. So whatever be the points, these are just calculate the gradients. That's a differentiation. Okay, that's called as gradient descent. Okay, fine. So this is the basic formula of a line. We are going to use it in our linear regression also. And m is the slope, y equal to mx plus c. M is the slope, b is the intercept, or c is the intercept. Y is the predictor, x is the input. Okay, so if I write y equal to mx plus b, x is input, b is intercept, m is slope. This is what we need to predict y. Okay, and what we are going to do in machine learning algorithms are, we have to tune m and b. This I will make you learn ahead. That means we need to tune the value of m and b, because inputs are just like it will remain the same. Your data will remain the same inputs. The thing is, during model training, these two parameters are tuned, they are changed, they are updated. That's what during training it happens. So m and b, they are called as parameters. So we will be tuning the parameters in model training. And whatever be the best parameters, whatever be the best values of m and b are, they are put in the equation to predict y. Okay, that we are going to see ahead. Okay, not at the moment. So these are concepts are related to your line. Okay, all these equations, they are related to the line. Okay, fine. All right, most of the things are related to the line. Okay, so introduction I gave, gradient descent I told you. Okay, loss function I told you. All right, apart from that, hmm, okay, now let me share my entire screen. Okay, and we'll check the basics of calculus again. Okay, so here it is. Now, fine. Okay, so let me increase the size. So derivative, as I told, differentiation. It is a rate of change or slope of a line. Rate of change in physics, slope of line in geometry. Okay, and this is how you represent it. Change in y upon change in x, dy by dx. D is a small change in x and y both. That you call it as a slope. Okay, this is the diagram by the help of which you can understand. Okay, fine. So using this definition, we can calculate the slope between the 2 points. Okay, these are some examples. X square plus 3, if you take like slope, calculate the slope of a curve. X cube plus 3 is a x square plus 3 is a curve. Okay, so they have mentioned, here is the equation: x square plus 3, 1 comma 4 this point, 3 comma 12 this point. Okay, we are having 2 points, so we need to calculate the slope between 1 4 and 3 12. So it would be like y2 minus y1 upon x2 minus x1. This is how you calculate the slope. Okay, and y2, y1, x2, x1 all are given to you. Okay, this is x1, x2, sorry, x1, y1, that is 1 4. This is x2, y2, 3 and 12. Slope is y2 minus y1 upon x2 minus x1. Okay, So we are talking about rate of change. How do we calculate the slope at a point 14 to reveal the change at this particular point? See, one way is to find the nearest point, calculate their slopes relative to x, and take the average. But the calculus provides an easier way, more precise way. It computes the derivative. So computing derivative of a function is essentially the same as our original proposal. That means we are looking forward for infinitely small distance away from x, very small distance away from x, and this is how we do write it. Okay, as I mentioned now, like, okay, this dx and dy dx, very small change in y, very small change in x, we can write like this: y plus delta y, x plus x plus delta x, where delta is a very small change in x and y both. So we are talking about this small change. That's called as a derivative. dy by dx. Okay, fine. So if we are available with the equation, that's what they are saying, x square plus 3. We will be doing dy by dx. That means if we put a small change in y with respect to x, we are going to get 2x. You know the differentiation of x to the power n is n x to the power n minus 1. Okay, and what point we are considering? The point we are considering is 1 comma 4. So here I don't have any y coordinate present, so I do have x equal to 1. I can put it here. So it's 2. Okay, it's 2. Fine. You can see that now again. Yes, yeah, here it is. In this way, derivatives helps us to answer the question, how does fx change if we make a very, very tiny increase to x? That means how does y change if we put a small change in x? Okay. In other words, derivative helps to estimate the slope between the 2 points. See, del, again, it's quite easy to understand what I'm writing. Del y upon del x, what does it mean? What is del? Del is the difference between 2 points, y2 minus y1. And del x is the difference between the 2 points, x2 minus x1. And that's the reason in your graph also here, okay, I will not say graph, it's a plot. In this particular plot, it considered 2 points like 1 4 and 3 12 which are closer to each other. So if the 2 points are closer to each other, and I will take the difference between the coordinate of x and coordinate of y, that will represent del y by del x, and that is called as a differentiation derivative. That's it. अच्छा, इतना बताया नहीं किसी ने, हाँ पता भी था हमको, ये कुछ नया नहीं है. The one which you are studying, slope, in your maths also you have studied y2 minus y1 upon x2 minus x1, this is slope. And they do write like, okay, del y by del x, and the small change only we are saying it as a gradient. This small change itself is a gradient. Okay, fine. So because small stones, na, that's what calculus is, small stones. Fine. So that is how we can estimate the slope between the 2 points, which are at a very small distance from each other. So in math language, we represent infinitely small increase using a limit. Yeah, limit is also one of the concept. Okay, I hope you understand about limits also. Okay, limit is defined as the output value as a function approaches towards approaches as a output value as the function approaches towards the input value. Okay, so I hope you remember these terms like limit extends to like 0, limit extends to 0. If this is a function given to you like x square plus 1, x tends to 0, we'll put x equal to 0. So it will be like, okay, what it will be like? 0 cos square plus 1. Okay, so answer will be 1. Something like this. Okay, we have studied the limits. Okay, so here, if you are available with the function x square and increment in x, that means very small increment, delta x, and let us suppose it is h. So if f of x is equal to x square, so f of x plus h will be x plus h ka whole square. That will be a plus b ka whole square. That means a square plus 2ab plus b square. Okay, and what I need to do is, this is my function f of x plus h, and let us suppose, okay, this is my initial, this is my next. Okay, so what I'm going to do here is, let's subtract from this by this by using slope. Okay, why? What's the reason? The reason is, you have considered h equal to delta x. This is my y, this is also my y. Let us consider y dash. So y dash minus y is the change in y. H equal to already delta x. Okay. So obviously what I need to do is, if I need to calculate the slope, I need to put them in a formula: x plus h ka whole square minus h square divided by h. That's what I need to do. You can open up the formula. Okay, so it will be like x square plus 2xh plus h square minus h square upon h. So this will cancel out. X you can take common. Okay, what you can take common? This will cancel. How you are going to cancel h now? How you can cancel x? H. Okay, here it is. Okay, this is 2xh h square x. Okay, you can take the common. Okay, x square. This is x square, not h square. So x square get cancelled. Okay, so you are having 2xh plus h square divided by h. Take h common from the top. Okay, numerator, cancel h and h. So you are getting 2x plus h, and h tends to 0. Here you can put a limit. H tends to 0, and put the value of h equal to 0 here. So only you are left with 2x. This is the answer. This is differentiation by using limits. Okay, so ultimately, what you studied in differentiation is rate of change and small. You are having y, you are having x. Just apply the concept on these. Okay, so that is what you are, this is the formula of limit. And we got 2x. Differentiation of x square is 2x using limits. Okay, so machine learning use cases where we are going to use the differentiation. I already told, in optimization algorithms like gradient descent, where we are going to look out for increase or decrease in the weights. Wait, one equation I have already mentioned. Okay, like this: w dash is equal to w minus alpha del L by del W. Here W is the older weight. Del L by del W, this is the gradient, and L is the loss or error. And we are differentiating error with the weight of the neuron in order to reduce it. Multiplying by learning rate. This is LR, learning rate. So this is a generalized equation in neural network for optimization. Okay, very important, and we are going to use it. Fine. Okay, then in chain rule also, we have to perform chain rule, and you know that, you know this thing. Df by dx is equal to dh by dg into dg by dx. Okay, I think they done something. It's better, let me write from my side. Df by dh is equal to df by dg into dg by dh. So ultimately dg will be cancel off, so we'll be having df by dh, but we are not going to cancel them off. Okay, now this is a differentiation with respect to g, and this is the differentiation with respect to h of g. Okay, so that's a chain rule. We can multiply various different differential components. Chain rule. Okay, in optimization also this will be applicable. Chain rule. Okay, so, and later I will tell, it's having a good scope in deep learning. Okay, fine. So yeah, here you are having one more example. Differentiation of x square is 2x. Okay, for x cube it is 3x square. Okay, for x cube it is 3x square. Now actually they gave you a question, like if you are having two functions, x cube and x square, and f of x equal to hgx, that means x square to the power 3. What is the derivative of f of x? What is the derivative of f of x? So you are having two functions, h and g. Okay, this is the main function that is composed of two functions, this and this. Okay, it's just slighter twist, but it's not like a tough one. And they have defined that f of x is equal to h of g of x. H of g of x means just put the value of g of x inside h. So x square will be put inside it, x cube. So it will be ultimately like this, x square, like this. So this is 3 2s are 6. And if you do talk about the differentiation of x ki power 6, it will be 6 x ki power 6 minus 1, that is 5. That should be the answer. A very simple example they have mentioned, 6 x ki power 5. So we can have a multiple functions inside. That's what we can have. Okay, and we'll be using this concept in our linear regression algorithm. Okay, for just like this. Okay, for example, you are having e ki power x square. Okay, e ki power x square. That means you are having e ki power a, and you are writing a equal to x square. So as you know, the differentiation of e ki power x is e ki power x, and the differentiation of x square is 2x. Okay, that's what the differentiations are. Okay, so here we can apply the chain rule. If you want to take e ki power, okay, if you consider x square equal to a, so it will be e ki power a. So we will be writing del e ki power a upon del a dot del a by del x. So what is a? What is a? X square. So here del e ki power a upon del a, will the answer is e ki power a dot. What is the differentiation of x square? That is 2x. Now replace again a with x square. So this is the answer. So chain rule or function inside the function, that's a lot of stuff we have done in our schooling, calculus में. The differentiation बहुत कुछ करा है. We did that. Okay, and the calculus is what I believe I studied in the 12th standard of my. Okay, so I think 40 to 40 marks, like differentiation and integration. Out of 100, 40 marks are for this thing only, calculus. The entire 12th syllabus, like calculus में फिर वो आपका limits हो गया, differentiation हो गया, okay, and differentiation limits हो गया, differentiability. Okay, limits, differentiability, functions. We start studying from function. function, then limits, then differentiation, differentiability, differential calculus, integral calculus. Okay, all these things we study. Okay, now what next it is saying? Gradient, okay, fine. I already told you. Gradient, these are the partial derivatives. Gradient is a vector that store the partial derivative of multivariable variable functions. And we do calculate the gradients only. Del y by del x, del partial differentiation, that's like gradients. And descent, opposite direction of the gradient. Okay, like this. For example, gradient of multivariate variate function. So 2z cube x square. Here I am having z and x both. So if I will differentiate with z, in that particular case, if I'm going to differentiate this function with respect to z, in that particular case, x will be constant. And when I will be differentiating this with respect to x, z will be constant. Okay, so if I perform del f by del x, okay, so just check the function 2z cube x square, 2z cube x square. This is my function. So if I differentiate df by dx, in that particular case, z cube will be constant. So 2z cube dot differentiate x square. So x square differentiation is 2x. So my answer will be 2 into 2 is 4 x z cube. And if I do df by dz, in that particular case, x square is constant. Then differentiate this z term, it will be 6z square x square. This will be the answer. Okay, fine. So, yes, we do use this concepts also. Fine. All right. Okay. Now, what next it is saying? Okay, let's talk about the integration now. One more thing I will explain, but it will take some time. Okay, that is maxima and the minima. Okay, very, very important concept that would take some time, but I will elaborate that. Let's discuss about integration now. Integration is the area under the curve. Okay, what you are doing in integration, you are collecting all the small points. It's a collection. So it's area under the curve ultimately. Okay, so here the diagram is built. Integration of function f from a to b. Okay, so from this point to this point, just cover the entire area. That is integration. Area under the curve. Okay, so the area AB is bounded by the function f of x. Okay, and we are going to take it from A to B. So the points x equal to A, x equal to B are called as limits of integration. Okay, now. So this is lower limit, this is upper limit. And from lower limit to upper limit, we are moving. So that's the reason we are capturing the entire area of the function. Okay, fine. So yes, that's how we do, right? Now, f of c correspond to area calculation of function of the upper limit of integration, like okay, from 0 to c, f of x dx. They have taken lower limit as 0, upper limit as c. There are two variables here. One is constant in this formula, that is 0. The input variable c describes the upper limit. 0 is the lower limit. The constant 0 describes the lower limit. Okay, note that choosing x equal to 0 from the starting point of the integral function was an arbitrary choice. It's not mandatory that we are always going to start from the 0. No. All right. So it's an arbitrary choice. You can take anything. Okay. Got it? Fine. So, yes. Huh. This is also one of the representation. And just like we are calculating the area, and see this diagram, we are saying we are going to capture the area, this portion. Okay, so we are taking the integration from a to b f of x dx, that is equal to f of b minus f of a. So this is my entire b. Okay, that means taking from 0 to b, entire b. And this is my f of a, that means taking 0 to a. So if we subtract this portion from this entire portion, I will be left with this portion. They are absolutely right. There's no mistake. There is not at all any mistake here. Okay, you can elaborate like this: integration of f of x dx, that means from a to b, that is equal to f of b minus f of a. Okay, so here I am looking forward for certain bounded region, certain bounded region. Okay, this is a, this is b. So b is from this axis, now this origin, this is b. A A is till here. So I need to require this thing. So obviously b minus a, that is the integration. Okay. Also, computing integration, again we are collecting small strips. Small strip. Okay. This also I explain you. If you are doing the integration here, that means like this. So you are collecting the small strips. That means this one. This is your dx, and this entire is y. So area of this strip is y dx. Just assume it's y dx. And from here to here, you have to calculate the area. That's why I am putting integration a to b. That means collect all these strips. Find the area of all these strips, and later on you combine. That is considering from a to b. So we are taking a very small strip. This is a very small strip, and the length of this strip is dx. The length of this strip is dx, and obviously this is y. This is y. So y into dx, like na area, area of a rectangle. What the area of a rectangle? Length into breadth. So if this is dx and this is your y, so y into dx. And now for entire area a to b, that's what they are explaining here. Okay, they have done some complex kind of work. I have explained you in a very simple way what we do in case of strip. Okay, so integration is opposite of differentiation. All right. So if you are differentiating x square, you will get x, and if you are integrating x, you will get x square plus some constant term. Um, okay, plus some constant term also. If you are performing indefinite integration. See, integration is of also of two types. One is definite, one is indefinite. Whatever you are seeing in this way, this is definite integration from a to b. Okay, when you are having upper limit and the lower limit. In case if you are not having the limits, you just simply have written integration of x, that will be x square plus c, constant. We have to add a constant. Okay, fine. So yes, there are few more things related to the differentiation and integration has been there. Okay, along with the major concept, that is maxima and the minima. And gradient I will again recall, because this is what we have to study: gradient descent. And we'll be performing such concepts in our algorithms optimization. So this calculus differentiation is important. Integration is also used, but let me tell you, 90% of usage of calculus in machine learning is differentiation. Very less where integration is used, very less. The entire is your differentiation only. Okay, so we'll focus more on this. All right, fine, cool. So let me stop presenting. Let me